Thomson's atomic model states atom is indivisible. But this model was rejected soon after the discovery of electrons and protons. Thomson's atomic model states the presence of positive and negative charges in an atom. In this model, it was believed that the negatively charged electrons resemble with the seeds of watermelon and remain embedded in an atom, whereas the positive charge is spread all over the atom and it resembles the red edible part of watermelon. However, it was rejected in the absence of any experimental evidence in its support. On the basis of Rutherford's scattering experiment, Rutherford proposed an atomic model. It states that a positively charged nucleus is present in the center of an atom and electrons revolve around the nucleus at high speeds in circular paths called orbits. But this model failed due to the reasons shown on the screen. Drawbacks of Rutherford's model: unable to explain stability of an atom, unable to explain the distribution of electrons around the nucleus and their energies, unable to explain line spectra of atoms. As a result, Bohr's model of an atom came into existence.
ਵਿਦਿਆਰਥੀਓ, ਤੁਹਾਡਾ ਅੱਜ ਦੀ ਕਲਾਸ ਵਿੱਚ ਸਵਾਗਤ ਹੈ। ਸਾਡਾ ਅੱਜ ਦਾ ਪਾਠ ਬੋਹਰਸ ਮਾਡਲ ਆਫ ਐਨ ਐਟਮ ਹੈ। ਪਰ ਅੱਜ ਦੇ ਇਸ ਵਿਸ਼ੇ ਤੇ ਵਿਚਾਰ ਕਰਨ ਤੋਂ ਪਹਿਲਾਂ ਆਓ ਪਾਠ ਦੇ ਲਰਨਿੰਗ ਆਬਜੈਕਟਿਵਸ ਨੂੰ ਜਾਣ ਲਈਏ।
On completion of this topic, learners will be able to describe Bohr's model of an atom, write postulates of Bohr's model of an atom, discuss achievements of Bohr's model, write shortcomings of Bohr's model of an atom, solve numerical problems.
ਵਿਦਿਆਰਥੀਓ, ਆਓ ਬੋਹਰਸ ਮਾਡਲ ਆਫ ਐਨ ਐਟਮ ਬਾਰੇ ਜਾਣੀਏ। ਬੋਹਰਸ ਮਾਡਲ ਆਫ ਐਨ ਐਟਮ। In 1913, Niels Bohr had given a model based on Planck's quantum theory, which is known as Bohr model of an atom. What are the postulates of Bohr's model of an atom? Let us discuss them one by one.
Postulates of Bohr's model of an atom. Let us take up first postulate. Electrons revolve around the nucleus in certain definite circular paths called orbits. इसका की मतलब है? Let us try to understand it in simple words. इसका मतलब है कि in each orbit, electrons have definite energy. These are also called energy shells or energy levels. These are also located at a fixed distance from the nucleus. These are numbered as 1, 2, 3, 4, and so on, starting from the nucleus and designated as K, L, M, N respectively. According to the second postulate, the energy of an electron in the orbit does not change with time. This model also states about the energy associated with each orbital around the nucleus and name them as E1, E2, E3, and E4, one after another. The increasing energy levels of various orbits are shown here. while in these specific orbits, an electron does not radiate energy. As we know, energy of an electron neither increases nor decreases in orbits. These are referred as stationary energy levels. Let us move on to the third postulate. Only those orbits are permitted in which the angular momentum of an electron orbiting around the nucleus is a whole number multiple of Planck's constant h divided by 2 pi. Let us try to understand it with the help of this animation. Suppose an electron of mass m is moving with velocity v in an orbit having radius r. Then angular momentum will be equal to mvr, which is again equal to nh upon 2 pi. Here, m represents mass of electron, v represents velocity of electron, r represents radius of the orbit, and h represents Planck's constant. The integer n can be used to designate an orbit. On placing value of n equal to 1, 2, 3, etc., we get h upon 2 pi, 2h upon 2 pi, and 3h upon 2 pi respectively. इत्थे याद रखन योग गल ए है कि there can be no fractional value of h upon 2 pi. ਦੂਜੇ ਸ਼ਬਦਾਂ ਵਿੱਚ ਅਸੀਂ ਕਹਿ ਸਕਦੇ ਹਾਂ ਕਿ the angular quantum number is quantized. Now the fourth postulate is the energy is absorbed or emitted only when an electron jumps from one energy level to another. Emission of energy and absorption of energy is also shown here. Electron is said to be in the ground state when it remains present in lowest energy level. What happens when an electron absorbs one quantum or one photon of energy? When an electron absorbs one quantum or one photon of energy, it jumps to a higher energy level, resulting in an absorption spectrum. At this position, the electron is said to have an excited state. When an electron jumps from higher energy level to lower energy level, it emits energy resulting in an emission spectrum. The quanta or photons of energy absorbed or emitted can be calculated by subtracting value of lower energy level from higher energy level of the atom. Difference of energy in two orbits is shown here. When an electron present in higher energy level emits photon, it comes to lower energy level.
Let us see the achievements of Bohr's model of an atom. Bohr's model can explain the stability of an atom, calculate the energy of an electron in a particular orbit of hydrogen atom and hydrogen-like ions, calculate the radius of each orbit of the hydrogen atom and hydrogen-like ions, explain the atomic spectrum of hydrogen, calculate the wavelength of the radiation emitted in transition between orbits. Let us take the first one, stability of an atom. According to Bohr's theory, an electron cannot lose energy as long as it stays in a particular orbit. Therefore, the question of losing energy continuously and falling into the nucleus does not arise.
Let us calculate energy of electron in a particular orbit for hydrogen atom. Energy of electron in a particular orbit of hydrogen atom can be calculated by using following formula. En is equal to minus 2 pi square me raised to power 4 upon n square h square for hydrogen atom. Here n is the number of orbit, or En is equal to minus RH into 1 upon n square. Here RH is known as Rydberg constant, which is equal to 2.18 into 10 raised to the power minus 18 joules per atom, or 1311.8 kilojoules per mole. On simplifying, we get En is equal to minus 1311.8 upon n square kilojoules per mole for hydrogen atom. On placing value of n is equal to 1, 2, 3, etc., we can calculate energy of electrons in various orbits. Let us also calculate energy of electron in a particular orbit for hydrogen-like ions. Bohr's theory can be applied to the ions containing only one electron, like monopositive helium, dipositive lithium, tripositive beryllium. The energy associated with these kinds of ions is given by expression En is equal to minus 1311.8 into Z square upon n square kilojoules per mole. Here, Z represents the nuclear charge, which is equal to atomic number.
The important thing to be noticed in these expressions pertaining to energy is that the value of energy is negative. Now, what is the significance of negative value of energy? The energy of an electron at infinity is arbitrarily assumed to be 0. This state is called zero energy state. Can you guess really what happens when an electron moves? Let me tell you. When an electron moves under the influence of nucleus, then due to attraction, it does some work and spends its energy in this process. Finally, the energy of the electron decreases and it becomes less than 0. It means that it acquires a negative value.
Let us discuss how Bohr model helps in the calculation of radii of orbits of the hydrogen atom. ਇੱਥੇ ਦਿਖਾਏ ਜਾ ਰਹੇ ਫਾਰਮੂਲੇ ਦੀ ਵਰਤੋਂ ਕਰਦਿਆਂ radius of orbit can be calculated. According to Bohr's model, radius of nth orbit is Rn is equal to n square h square upon 4 pi square me square z, which is again equal to n square a naught. On substituting the values of various constants, we get Rn is equal to n square into 52.9 picometers. Here n is the number of orbit. On placing value of n is equal to 1, 2, 3, and so on, we can calculate radius of various orbits. As it is clear from this formula, value of Rn is proportional to value of n. As value of n increases, value of Rn also increases. Now let us have a look at the calculation of radii of orbits of hydrogen-like ions using Bohr's model of an atom. Bohr's theory can also be applied to the ions containing only one electron, like monopositive helium, dipositive lithium, tripositive beryllium, etc. The radii are calculated by the expression Rn is equal to 52.9 n square upon z picometer. Here, Z represents the nuclear charge, which is equal to atomic number. Let us see how Bohr's model explains the atomic spectrum of hydrogen. We know when required amount of energy is absorbed by the electron, an electron will move from a lower stationary state to a higher stationary state. But energy is emitted when an electron moves from a higher stationary state to a lower stationary state. And the difference of energy, delta E, is equal to E2 minus E1. Here, E2 is the energy associated with higher energy level and E1 is the energy associated with lower energy level.
When an electric discharge is passed through gaseous hydrogen, hydrogen molecules dissociate and produce energetically excited hydrogen atoms. The electrons present in different hydrogen atoms absorb different amounts of energies and are excited to different energy levels. Since the lifetime of electrons in these excited energy levels is very small, they return to some lower energy levels or even to the ground state in one or more jumps. Thus, different excited electrons adopt different routes to return. As a result, they emit different amounts of energies and thus produce a large number of lines in the atomic spectrum of hydrogen. The hydrogen spectrum consists of several series of lines named after their discoverers.
Various transition series are Lyman series, Balmer series, Bastian series, Brackett series, and Fund series. This animation shows jumping of an electron from n equals to 6 energy state to n equals to 1 energy state, n equals to 5 to n equals to 1 energy state, n equals to 4 to n equals to 1 energy state, n equals to 3 to n equals to 1 energy state, n equals to 2 to n equals to 1 energy state. All these form Lyman series. When an electron returns to second energy level, Balmer series is obtained. In Balmer series, jumping of an electron from n equals to 6 to n equals to 2, n equals to 5 to n equals to 2, n equals to 4 to n equals to 2, n equals to 3 to n equals to 2 is shown here. When an electron returns to third energy level, Bastian series is obtained. In Paschen series, transition of electron from n equals to 6 to n equals to 3, n equals to 5 to n equals to 3, n equals to 4 to n equals to 3 is shown. When an electron returns to fourth energy level, bracket series is obtained. In bracket series, transition from n equals to 6 to n equals to 4, n equals to 5 to n equals to 4 is also shown. When an electron returns to fifth energy level, Fund series is obtained. In Fund series, transition of electrons from n equals to 6 to n equals to 5 is shown here. Let us solve one numerical. Calculate the energy associated with the first orbital of monopositive helium. What is the radius of this orbit? Solution. En is equal to minus 1311.8 into Z square upon n square kilojoules per mole. For monopositive helium ion, N is equal to 1, Z is equal to 2. E1 is equal to minus 1311.8 into 2 square upon 1 square kilojoules per mole. It is equal to minus 5247.2 kilojoules per mole. The radius of the orbit is written as Rn is equal to 52.9 n square upon Z picometer. Since value of n is equal to 1 and value of Z is equal to 2, Rn is equal to 52.9 picometer into 1 square upon 2, which is equal to 26.45 picometer. Derivation of Rydberg's equation. When an electron jumps from a lower stationary state to a higher stationary state, the amount of energy absorbed or emitted is written as delta E is equal to E2 minus E1. Here, E2 is the energy associated with higher energy level and E1 is the energy associated with lower energy level. Now E1 is equal to minus RH into 1 upon N1 square and E2 is equal to minus RH into 1 upon N2 square. Now substitute the values of E1 and E2 in shown equation. Delta E is equal to E2 minus E1. Thus we get delta E is equal to minus RH into 1 upon N2 square minus RH into 1 upon N1 square. This further reduces to RH into 1 upon N1 square minus 1 upon N2 square. And let us number this equation as 1. After substituting the value of Rydberg constant, we get delta E is equal to 2.18 into 10 raised to the power minus 18 joules into 1 upon N1 square minus 1 upon N2 square. Now, the frequency nu associated with the absorption or emission of photon will be delta E is equal to h nu or we can write it as nu is equal to delta E upon h. Let us number this equation as 2. Now put the value of delta E from equation 1 to equation 2. We get nu is equal to RH upon h into 1 upon n1 square minus 1 upon n2 square. Further, put the values of Rydberg constant as 2.18 into 10 raised to the power minus 18 joules and Planck's constant as 6.626 into 10 raised to the power minus 34 joules second. We get nu is equal to 3.29 into 10 raised to the power 15 into 1 upon n1 square minus 1 upon n2 square Hertz. Now in terms of wave number, that is nu bar. Now nu bar is equal to nu upon c. Here c is velocity of light. This further is equal to RH upon hc into 1 upon n1 square minus 1 upon n2 square. On substituting the value of Rydberg constant and velocity of light, finally we get 1.09677 into 10 raised to the power 7 into 1 upon n1 square minus 1 upon n2 square meter inverse. In case of absorption spectrum, n2 is greater than n1. The term 1 upon n1 square minus 1 upon n2 square becomes positive, so that delta E is positive and hence energy is absorbed. In case of emission spectrum, n2 is smaller than n1. The term 1 upon n1 square minus 1 upon n2 square becomes negative, so that delta E is negative and hence energy is released.
Let us try to solve one more numerical problem. What are the frequency and wavelength of a photon emitted during a transition from n equals to 5 state to the n equals to 2 state in the hydrogen atom? And the solution is, since n2 is equal to 5 and n1 is equal to 2, this transition gives rise to a spectral line in the visible region of the Balmer series. 1 upon lambda is equal to RH into 1 upon n1 square minus 1 upon n2 square. It is equal to 109,677 multiplied by 1 upon 2 square minus 1 upon 5 square, which is equal to 109,677 multiplied by 21 upon 100. Its value comes out to be 23,032.59 per centimeter. So, lambda is equal to 1 upon 23,032.59 centimeter inverse. It is equal to 434 into 10 raised to the power minus 7 centimeter, which is equal to 434 into 10 raised to the power minus 9 meters. It is equal to 434 nanometers. Now, frequency of the photon is given by nu. Nu is equal to c upon lambda. Nu is equal to 3 multiplied by 10 raised to the power 8 meter per second upon 434 into 10 raised to the power minus 9 meter, which is equal to 6.91 multiplied by 10 raised to the power 14 per second. Its value comes out to be 6.9 into 10 raised to the power 14 Hertz. Let us discuss shortcomings of Bohr's model of an atom. Bohr's theory was unable to explain atomic spectrum for atoms containing more than one electron. The wave nature of the electron is not considered in Bohr's model. As per Bohr's model, an orbital is a clearly defined path, and this path can be defined only if the position and the velocity of the electron are known exactly at the same time. But this is not possible according to Heisenberg's uncertainty principle. It fails to explain dual nature of matter. Bohr's model failed to explain the ability of atoms to form molecules by chemical bonds. Bohr's theory was not able to explain effects like Lyman effect and Stark effect, that is, splitting of lines in the magnetic field and electric field respectively. Students, I hope you enjoyed the lesson as much as I did, and you look forward to the next class. Thank you for your attention and see you next time.